Welcome to the video solution guide to problem number 9 of the linear kinematics assignment. As per usual, I think a good place to start for this problem is to draw a picture. So we have a baseball which is hit from a baseball bat at a height of 1.2 meters off the ground. So that's the side view of the baseball bat. The ball is hit with an unknown initial velocity, but once it leaves the bat, it makes an angle of 46 degrees relative to the horizontal. The baseball travels a distance of 125 meters, where it just clears a wall that is 3 meters tall. So this horizontal distance here is 125 meters. And the problem is asking us to find this unknown initial velocity, VI. A good place to start is to write out everything we know in both the x and the y directions. We know that the baseball travels 125 meters, so delta Rx equals 125. We know that the change in height of the baseball, so delta Ry, is equal to 3 minus 1.2, which gives us 1.8 meters. And if we're confused about the sign, whether these values are positive or negative, we can think of a positive value in the x direction as anything to the right of the origin, which we'll define right at where the baseball is hit. And then a vertical displacement, or positive y value, will be anything traveling upwards of where the baseball is hit at 1.2 meters. Okay, the initial velocity in the x direction is unknown. The initial velocity in the y direction is also unknown. And that's what we'll be solving for, both of those two values. We know that the final velocity in the x direction is equal to the initial velocity in the x direction, because we're neglecting air resistance. The final velocity in the y direction is also unknown. We're assuming that there's no air resistance, so the acceleration in the x direction is equal to 0. And for simplicity's sake, we'll say that the acceleration in the y direction is equal to negative 10 meters per second squared. Additionally, we are uncertain at this time of how long the ball is in the air, so time is also unknown. A good place to start for solving the unknown initial velocity are the equations that describe the change in displacement. So that the change in the horizontal displacement is equal to the initial velocity in the x direction times time. That's the first equation. And we also know that the change in vertical displacement is equal to the initial velocity in the y direction times time plus 1/2 the acceleration in y times t squared. We can see right away that we will need more information to solve this problem. We don't know the time that has elapsed, and we don't know the vertical and horizontal velocities still. But what we can do is we can use information about the takeoff angle, namely that the tangent of the angle, tangent of theta, which is equal to 46 degrees, is equal to the ratio of the vertical velocity over the horizontal velocity. And now what we can do is we'll rearrange equation 1 and solve for the horizontal velocity in the x direction. So that's going to equal the displacement in x divided by time, and we'll rearrange this equation as well, solving for the initial velocity in x as well, which will equal the initial velocity in y divided by the tangent of the angle. It should be apparent that we can equate these two equations and solve for one of the unknowns, which is time. When we do that, we see that t, time, is equal to the change in displacement in x times tangent of theta divided by the initial velocity in y, and we get this just by doing some basic rearranging of the equations on the left and on the right. At this point, we'll go back into equation 2, and I'll write that again as a reminder. So the change in height in the y direction is equal to the initial velocity in y times time plus 1/2 the acceleration in y times squared. At this point, we have two equations, so equation star and equation 2, with essentially one unknown. And we can solve that unknown by plugging in our equation for time, t, wherever t is present in equation number 2. So let's go ahead and do that. So delta ry, change in height in the y direction, is equal to initial velocity in y times time, and we'll write in this as delta rx times tangent theta divided by initial velocity in y plus 1/2 acceleration in y times squared. Oops, and what we want to do actually is we want to write this time as delta rx, change in displacement in x direction, times tangent of theta divided by initial velocity in y, and that quantity is squared. So let's look through this equation. We know the change in height in the y direction, 1.8 meters. We can cancel this initial velocity in y with this initial velocity in y, and we know the change in displacement in the x direction. We know the tangent of angle theta. We know the acceleration in y, and again we know the change in displacement in x, tangent of theta. We don't know is this initial velocity in the y direction, but we know everything else. So we can rearrange this equation, and we can solve for the initial velocity in the y direction. And when we do, we find that the initial velocity in the y direction is equal to 25.2 meters per second. And I've assumed that the acceleration in the y direction is equal to negative 10 meters per second squared, rather than negative 9.81. So when you do this problem on your own, be sure to use negative 10 as your acceleration in the y direction. And the last and final step is to find the resultant velocity. The easiest way to solve for this resultant velocity is we can draw our right-hand triangle again, and we'll note that this is the initial velocity in y, this is the initial velocity in x, and this is the angle theta. We know that the sine of angle theta is going to equal the opposite side of the triangle divided by the hypotenuse of the triangle, or in other words, the sine of 46 degrees will equal the initial velocity in y divided by the resultant velocity. And here the initial velocity in y is what we found previously, 25.2 meters per second. I'm not sure why that traveled with us. Rearranging and solving for the resultant, we get 35 meters per second as the resultant takeoff velocity, and that's the answer to the problem.